All right, we're looking at an exam question here. We're in the lab, apparently. We mix two liquids together. We're holding that flask, and it becomes noticeably colder, okay? The first question we're asked is about the sign of delta H of the solution for that process, and we're asked if it's positive or negative. All right, so that comes directly from the information that it's gotten noticeably colder. Okay, so that means that delta H of the solution must have been positive. In other words, it was an endothermic process. Okay, so to make this thing happen, to make this solution, this mixing process happen, we needed to absorb, and by we, I mean now I am the molecules in that liquid flask. We need to absorb that thermal energy. And so some of that thermal energy is converted into making these new interactions, which apparently cost us energy. That's why it's endothermic, and that's why it feels cold, because we used one form of energy and we converted it to another, and that means that we're feeling that loss of energy into or that conversion of thermal energy into something else. Okay, so that's endothermic. It's a positive number, and the flask will feel cold. All right. The next question is the sum of delta H solvent and delta H solute must have been, and then this is, I think, bigger, smaller. Let me just make sure I know exactly what I'm asking you guys. Oh, it's just greater or smaller. Is it greater or smaller? Smaller than the absolute value of delta H mix. Okay, so let's remind ourselves where those terms come from and how they relate. Delta H of the solution we already know is positive. It equals delta H solvent plus delta H solute plus delta H mix. These two are always going to be positive, right? That is the cost of breaking up our AA interactions and our BB interactions, okay? This is always negative. Just draw a negative sign. And it is the sort of benefit, the payout of mixing and creating interactions between A and B molecules. All right, so we have to put in energy to break up AA. So AA is lower in energy than A infinitely separated from another A. Okay, so that's why this is positive, because we have to put the energy in to break those apart. Okay, they wouldn't be next to each other. They wouldn't be hanging out if it didn't benefit them energetically. So they come together, their energy is lowered, and then we yank them apart because instead of mixing with A, we want to try and mix it with B. So the same thing is true for B, right? We have to put in energy. That's why this is positive, right? But now on this other part, when we mix, this is where the payout is, right? We have A and B infinitely separated, and we're wondering, is the payout of this worth it or not? Okay, so those are infinitely separated, and now we get to make interactions, IMFs, between these two, and that releases energy. So that's our exothermic process. This is endo. All right, we already have a bunch of information and by bunch, I just mean we know that it's cold, and so it has to be endothermic. That means that this number, this sum, must have been greater than the absolute value of that delta H mix. Okay, so this had to have been a larger number than the positive value of that delta H mix. In other words, it cost us more to break A and B apart than we earned. Now I'm sort of thinking about this as like a money transaction, than we earned by bringing A and B together. This process still happened, right? We noted that the two liquids mixed, even though it was cold, even though it was endothermic, which tells us that this was driven by entropy. Even though we didn't sort of get our energy out that we put into it, right? We ended up making it less stable from an enthalpy perspective. We still got to mix it up. We still increased the disorder of the universe, which is an entropy consideration, which pushed this forward. So you might be under it's easy to assume that, hey, because it's endothermic, this process would never happen. As long as it's only slightly endothermic, right? Like as long as that number is not like a super duper enormous positive number, if it's close to zero, this mixing process can still happen. It's pushed forward by entropy. And we will get into that balance of like when does it happen and when doesn't it happen? In other words, when is it spontaneous? In chapter 19, which is towards the end of the semester, but we'll come back and we can understand it through the lens of a balance between entropy and enthalpy, which I know you are just like so excited for.